This is 4.3, graphs of polynomial functions. We are going to be looking at the shape of basic polynomial functions and also describe the end behavior. All right, so polynomial functions can be described using many different categories. Continuity, even versus odd, end behavior, intercepts, local extrema, points of inflection, and we can use their multiplicity to find things out about them too. So let's start with continuity. Every graph of a polynomial function is continuous. It is an unbroken curve with no jumps, gaps, or holes. Also, the graphs have no sharp corners. So if you look over here at these two little graphs, you can see there's a jump, there's a hole, there's sharp corners, there's gaps. So those would not represent polynomial functions. Polynomial functions will be continuous if you were to graph them. All right, polynomial functions can be even or odd. So even or odd is mostly described by their end behavior. So if the graph goes up at both ends or goes down at both ends, that means we have an even graph. If your polynomial graph goes down on one side, up on the other, vice versa, up on the left, down on the right, that means we have an odd function. So even and odd, where does that come from? Well, it comes from the power of the function. So the highest power, we have the degree. So a function of even degree, its highest power is going to be an even number. For example, x squared, or x to the fourth, or x to the sixth. Okay, so if the degree of the function is even, the highest power of that function is even, it's going to have the same end behavior. It'll either both ends going up or both ends going down. If a function has odd degree, your ends of the graph or the arrows are going to be going in opposite directions. Examples of odd functions would be like x cubed, x to the fifth, x to the seventh, x. Okay, so anything with an odd degree, the highest power is an odd number, means that one end is going down, one end is going up. They're going in opposite directions. All right, intercepts. The graph of a polynomial function of degree n has one y-intercept, which is equal to the constant term. So if you plug 0 in for x, you'll get that constant term out no matter what polynomial you have. X-intercepts, a polynomial will have at most n x-intercepts and could have no x-intercepts. So n, remember, is the degree of the function. So if our function is degree 4, it could have at most 4 x-intercepts. However, it is possible that it has none. If there are no x-intercepts, that means it's like a graph that's just kind of floating above or below that x-axis there. Number of local extrema. A polynomial function of degree n has at most n minus 1 local extrema. So if you have a third degree function, it will have at most 2 max or min values, and most likely one of each. Points of inflection, a polynomial of degree n has at most n minus 2, so it'll have one less point of inflection than it has extrema. So if our graph is degree 3, it will have 1 point of inflection. So one place where it changes concavity. So let's use these ideas, end behavior, intercepts, local extrema, and points of inflection, to describe what the graph of this would look like. So first, let's look at the end behavior. So let's figure out the degree of our function and figure out if it's even or odd, and then we'll be able to describe the end behavior. So if we look, f of x equals x plus 3 squared, x plus 1 to the first here, and then x minus 1 cubed. So really, if we were to expand this out, okay, this would expand out to a quadratic with degree 2, this would expand out to degree 1, and this would expand out to degree 3. So our total degree is 2 plus 1 plus 3. So our total degree is 6. All right, so it's an even degree. So since the degree is even, our end behavior would be both sides going either up or down, and we tell if they're both going up or down by whether it's a positive or negative. Well, this is positive, so end behavior, both ends will be going up. All right, next, we can also use the number of intercepts. So since this is a degree 6 at most, this will have exactly one y-intercept. So we know it'll have one y-intercept, and we can find that. So the y-intercept is if x is 0. So if x is 0, the y-intercept is going to happen at, let's see here, 3 squared times 1 times -1 cubed. So 9 times 1 is 9, times -1 is -9. So our y-intercept is 0, -9. And then x-intercepts, at most we will have, at most we will have 6, but it looks like here by how this is listed, we only have 3 because this is in factored form. So we have an x-intercept at -3, an x-intercept at -1, and an x-intercept at 1. So our x-intercepts are going to be -3, 0, -1, 0, and 1, 0. So if it's in factored form, that's how you can tell what your x-intercepts are. All right, then from there, we can describe the number of local extrema. So at most, this is going to have, since it's degree 6, at most it could have 5 local extrema. And then points of inflection. So following from that, at most, we would have 4 points of inflection. So we can specifically find the y-intercept by plugging x in. We can find the x-intercepts if it's in factored form, or use what you did in 4.2 and find your real roots using the possible rational roots.
Multiplicity is something that tells us how a graph behaves at the x-axis, or at its zeros, or its roots. So if C is a 0 of multiplicity k of a polynomial of function f of x, so for example, we have x minus c to the power of k. That's what that means. All right, k is the multiplicity, the power of that 0. If k is even, the graph of f just touches. So it's going to come down to the x-axis, touch, and then go back in the either up or down, depending on which way it's going. If k is odd, if that power is odd, it's going to cross. If that power is just 1, it will just cross the x-axis like that at one point. If it is like power of 3, you're going to see like a bend in it. So it'll kind of bend through like that, kind of like you would see if it was like a cubed function, okay? So there is a little bit of a difference. Some will just cross like that, and some will kind of bend through the x-axis there. Let's see what that looks like if we try and sketch a graph of this function down here. So first, let's state our zeros. Let's see what we have. So for zeros, we have 5, -1, and -7. All right, the multiplicity of 5 is 2, so it's even. The multiplicity of -1 is 1, so odd. And then the multiplicity of -7 is 3, so another odd. All right, so what does this tell us? On the x-axis then, that means at 5, the graph is just going to touch the x-axis. At -1, the graph is going to, since it's just a power of 1, it is going to just cross through the x-axis. And then at -7, that power of 3, that little higher power, means that it's going to cross, but it will bend. If we're going to be a little more specific, it'll bend through the x-axis there. All right, so now let's see if we can find out some other things about this so we can start graphing. All right. So let's figure out our end behavior first. We can use our powers to figure out what our end behavior would be. So our end behavior is, let's see, a power of 2, 1, and 3. That's going to be a power of 6. So this is degree 6, and it's positive. So our end behavior is going to go up on either side. So we can kind of start here. So over this way, it's going to be ending up, and over here, it's going to be ending up. And then we have our zeros at 5, -1, and -7. All right, so from here, we can start sketching our graph. And we can use our multiplicity and we can just sketch in any curves that we need to in between. So at -7, we have an odd multiplicity, so we're going to cross the x-axis with a bend, with a slight bend in it. So as you come down, you're going to kind of flatten out there and then bend through. And then at -1, we come back and just cross. We can just keep going up. Then we're going to cross the x-axis or the y-axis and then come down to 5 and touch and go back up. Okay. If you were asked to be specific, if they asked you to find the y-intercept, you could do that. Y-intercept would be when when x is 0. So f of 0 would be -5 squared times 1 times 7 cubed. Which gets you 8,575. So your y-intercept would be way up there at 8,575 if you wanted to be specific about that. Okay.
All right. Using that as a guide, why don't you try and sketch the graph of this function? So pause here and do that. So here's a rough sketch, very rough sketch. So zeros are 6, -2, 4, and 1. So I put those x-intercepts on the x-axis. Found my y-intercept to be way down at -1,152. So I put that there. And then this was a degree 7 and was odd, and it's negative. You can see it has this negative out front. So when it's negative, it's like it has a negative slope. So if you were to draw a line from arrow to arrow, you would have a line with a negative slope. So that's where that negative is shown in. So it goes up to the left, down to the right, like that. So that's how I got my end behavior. And then from there, we just sketch it in using our multiplicities. So at -2, we cross because -2 has an odd multiplicity. Go through our y-intercept, come back up and cross at +1, cross at +4, and then +6 had an even multiplicity of 2 there, so we cross right there. All right, so this is a possible sketch of this graph. All right, Next, let's just go through and see if we can figure out the degrees and base it on if they're odd or even, what's the smallest possible degree, how many real zeros, and then leading coefficients if they're positive or negative. If you want to pause here and try it on your own, you can. If you want to just keep listening and follow along, you can do that as well. So is each graph even or odd degree? So if you look here, we're going down to the left, up to the right. They're going opposite directions, so odd. Same thing in number 2. Odd. Number 3, they're both going down, so we're going to say even. And then 4, they're both going up, so that's an even degree. What is the smallest possible degree of each of these graphs? So what's going to help you do that the most, or help you do that the best? I usually use my max and min values. So if I have 2 local extrema right here, right, 1, 2, that means I can be 1 degree larger than that, right? So this is going to be degree 3. Now, you could have 2 max and mins and be like degree 6, but it's asking for the smallest possible degree. It could be greater than degree 3, but at least it has to be degree 3. Here, if we count all of our local extrema, 1, 2, 3, 4. So that means add 1 to that. So at least it has to be degree 5, at least. All right, 1, 2, 3. So at least this would have to be degree 4. And then if you look here, 1, 2, 3. So at least this would have to be degree 4. And it kind of makes sense, right? So if you look here, this would represent an odd function. So degree 3, yeah, that would make sense. Could be degree 5, could be degree 7, but at least degree 3. And then look at the end behavior here. It's going to have to be odd. So at least degree 5, could be 7, could be 9. Here, this is an even function, so degree 4 would make sense. And here, this is an even function, so degree 4 would make sense. How many real zeros does each graph have? Okay, real zeros, those correspond to real roots, x-intercepts, that fun stuff. So if we look here, 1, 2. So this has 2 real zeros. And then if we look here, this graph has 1, 2, 3. 3 real zeros. 1, 2. 2 real zeros. And then this graph has 1, 2, 3, 4 real zeros. Now, there could possibly be some imaginary zeros, especially at these portions that are either above or below the x-axis. We could have other zeros in there as well. But just based on the graph, those are the real zeros that we see. All right, and then here is the leading coefficient of each graph positive or negative. Well, we know this is an odd. And if we were to attach the arrows on either end, we would have a positive line. So this is going to be a positive leading coefficient. All right, this odd graph, if we attach the arrows, we see a negative line. So this would have a negative leading coefficient. This graph is even, and they're both pointing down, so that's going to be a negative leading coefficient. And this even function has end behavior pointing up on both sides, so that's going to be a positive leading coefficient. All right, so keeping these classifications of polynomials and their graphs in mind, go ahead and practice, ask your teacher if you need help, and then complete that LT check for today.